In this video, we're going to be talking about half-lives of nuclear isotopes. So half-life is something you've probably heard about before. Half-life is the time required for one half of the nuclei of a given sample of that isotope to disintegrate. So this is so stable and unchanging, we can look it up on references and we can use this half-life to determine things like the age of dinosaur fossils or geologic time. We can even use it to make clocks. The most stable clocks in the world are based on atomic decay. So the half-lives of selected isotopes can be found in Table N. So if you need to know a half-life of any element, you can look up the ones on Table N and use them to answer questions about how much time has passed or what fraction of a sample remains after a certain amount of time of decay. And these are some of the harder questions that are on the Regents, and they're really not that bad if you learn the process for how to do half-life questions. So let's do some examples. If the half-life of an isotope, potassium-42, is 12.4 hours, and if you had 100 grams of the isotope, how much would you have left after 37.2 hours? So this seems like a difficult word problem, but it's really not that hard if you just kind of tackle this question logically. So let's look at what's going on here. So one of the best solutions here is just to figure out how many half-lives have passed in this amount of time. So if we divide the total time by the half-life, so we have 37.2 hours, and it said the half-life of this isotope was 12.4 hours. That is 3 half-life periods that have gone by. So during the first half-life period, the following is going to occur. The 100-gram sample that we're going to start with is going to break down to 50 grams. During the second half-life, the 50-gram sample that we now have is going to break down by half. That's the definition for a half-life. It's going to break down in half to 25 grams. And then we have one more half-life to go through. The third half-life, that 25-gram sample, is going to decompose or decay down to 12.5 grams. So this is one way to do it, just kind of, attack the problem logically here. So a way I actually like better is what I call the chart method. So this is the chart method. In the past, on the Regents, on Table T, there was all sorts of equations. There was at least 2 or 3, maybe even 4 equations for doing nuclear chemistry problems like this. And they were kind of confusing and involved you having to raise things to fractions in your calculator, and it was challenging for a lot of kids, and nobody actually used it. So they ended up getting rid of it. It's not even on your reference table anymore because everybody uses this chart method. So let me show you how it works. So the first thing you need to do in your chart is make columns for the important information. So this question told you about the time that was involved, the mass. They gave you original mass, and we're asking you what mass remains. And you're always going to need to include half-life. This is how you're going to figure out how far down the chart you need to go. So whenever we do the chart method, we always start off at 0 half-lives. So no time has gone by, and the original mass is present at 0 time gone by, 0 half-lives. So that's 100 grams. So in the problem, it says that the half-life of this sample is 12.4 hours. So after one half-life, 12.4 hours has gone by, and that mass has decayed by half from 100 to 50. So after the second half-life, another 12.4 hours go by. So 12.4 plus 12.4 is 24.8 hours. And half of the remaining mass is going to be left after the decay, 50 down to 25. So I need to go one more half-life to get to 37.2 hours, which is what they said in the problem, and I'll have half of my remaining mass left. So the 25 grams is going to decay after the third half-life by half, down to 12.5. So that's the chart method. Let's do some more problems. Let me show you every which way they can ask you questions with a chart problem here. Okay, so sometimes I'll ask you about fractions. If 1/8 of a sample of radium-226 remains, how much time has passed? So remember, as always, we start with 0 half-lives, no time has gone by, and I'm going to have 100% of my sample, or if we're doing it in fractions, 1 out of 1. Okay, after the first half-life, I need to figure out how much time has gone past. So where do I check if I need to know the half-life for an isotope like radium-226? Table N. So you go to table N and you scan till you find radium-226, and you'll see that the half-life is 1,599 years. So after 1,599 years, I'm going to have half of my sample, as per the definition of half-life. It'll be 1/2 of my fraction remaining. Okay, so I need to know how much is going to be remaining after 1/8. So I need to keep going. So I'm going to keep going down my chart. After a second half-life, another 1,599 years has elapsed. So we're up to 3,198 years. 1/4 of my original amount will be there. And I know I need to go one more to get to 1/8. So the third half-life will bring us to another 1,599 years elapsing, to a total of 4,797 years. I will have 1/8 of my original sample remaining. So that is the answer, 4,797 years. Okay, let's look at another one. Iodine-131 has a half-life of 8.07 days. If a 10-gram sample was allowed to decay for 32 days, what fraction remains? So we'll start with 0 half-lives, no time has gone by, and the problem says that we have a 10-gram sample, so I'll have the full 10 grams, and I will have the 100% of it, or 1 out of 1, remaining. After the first half-life, it says the half-life is 8.07 days, so 8.07 days has gone by, and I'm going to have 5 grams remaining, and my fraction will be 1/2. So then we just keep following this chart down until I get to 32 days, or something close to that. So after the second half-life, another 8.07 days has elapsed, so 16.14 days. I'll have 2.5 grams and 1/4 remaining. After the third half-life, another 8.07 days go by, so we're up to 24.21. I'll have 1.25 grams remaining, and I'll have 1/8 fraction. And after the fourth half-life, another 8.07 days go by, so I'm up to 32.28, which is what it's being allowed to decay to. So it doesn't have to be exactly 32. If this is what it's close to, you're good. So the mass will be 1/2 of 1.25 grams, so we're down to 0.625 grams, and the fraction remains would be 1/16. So this might seem like a lot of work, like especially this mass column. This isn't really necessary for this question, because they're only asking about fraction. You can include this in your chart if you want, or you can skip this column. You really only need the columns that they're asking you for, but it never hurts to do extra columns. It's just going to give you more practice on doing this chart method correctly. Okay, so let's look at another problem. This one's slightly harder. A radioisotope has a half-life of 10 days. 1 gram remains after 40 days. What was the initial amount of the radioisotope? So this time I'm not working down the chart like I was in the previous examples, where I work down and my answer somewhere down here. They want to know what was the initial amount. So I'm on this one here. So let me show you how we can fill in this chart and eventually work our way up to get the initial amount. So 0 half-life, 0 time has gone by, and the mass we don't know. So I'm going to leave that blank. After the first half-life, it says 10 days has gone by. The half-life of this unknown isotope is 10 days. I still don't know the amount, so I'm going to leave this column blank. After the second half-life, 20 days have gone by. After the third half-life, 30 days have gone by. After the fourth half-life, 40 days have gone by. So it said in our problem, 1 gram remains after 40 days. So after 40 days, my mass is 1 gram. So now I just need to work backwards to get to the initial amount. So when we were working down the column, we were cutting our mass by half, because that's what the half-life is how much decays. Half of it decays each half-life. Now I'm just going to be working backwards. So I'm going to be doubling my mass working up the chart. So if this is 1 grams on the 4th half-life, on the 3rd half-life, it must have been 2 grams. And if it's 2 grams on the 3rd half-life, on the 2nd, it must have been 4. On the 1st, we would double that to 8. And at our initial time, with 0 half-lives, it must have been 16 grams. Okay, one more. 100 grams of radioactive or radioisotope decayed to 12.5 grams after 90.7 years. What was the half-life? So again, we're going to have to be working up. Our half-life was going to be in our time column. We actually want this one here. I want to know the time after 1 half-life has gone by. So let's look at how we start this one. So 100 grams of this isotope decays to 12.5 after 90.7 years. So we'll start with 0 half-lives. 0 time has gone by, and it says that I have 100 grams in my problem here. So I don't know the time yet, so I don't know my first half-life, but I know after my first half-life, my mass is going to decay down to 50 grams. After the second half-life, I'm going to decay that 50 grams into 25 grams. After the third half-life, I'll be down to the 12.5. Now it says after this 100 grams decays to 12.5 years, that happens in 90.7 years. So my time after the third half-life is 90.7 years. So now I need to work backwards to get to number 1 here. Okay, this is a little harder than doing mass. So how I would suggest that you're doing this is to take that total time here, 90.7 years, and divide that by the total number of half-lives that have gone by. We've done 3 half-lives. So 90.7 divided by 3 is 30.23 years. So that is our half-life here. We'll fill that in. And if you want to double check just to make sure that you did it right, if you're not sure, fill in the rest of the chart. And if it works, if you do 30.23 plus another 30.23, you'll get 60.46. And if you do 60.46 plus another half-life, 30.23, if you get 90.7, you know you're correct. And it is 90.7. So there's your answer. So in summary here, use the chart method whenever you are answering questions about half-life. It's a logical approach, and it's much easier. Now that you don't have the formulas in your reference table anymore, it's your only solution to doing these problems here, unless you want to look up the formulas on your own. Always start with 0 half-lives and 0 time. One of the biggest mistakes I see in students that get these questions wrong is not starting the chart at 0. If you need a half-life of an isotope, if that's not given to you in the problem, don't forget that's all found on table N. And you're going to need to know your fractions, at least up to 1 out of 32. So sometimes when you're asked these fraction questions, if you don't know which fractions come after which ones, you can get these questions wrong. And always work your way either up or down the chart, depending on the type of question being asked. Of course, these questions are pretty difficult, and if you're having trouble, don't worry, we'll be doing plenty of practice in class. But I just wanted to give you a bit of a head start here in looking at how to do these problems. And if you have any questions, we'll probably be doing lots of these in class, and eventually I promise you you'll get the hang of it.